So today is review. Interaction with many of you about projects or homework questions or things about studying for the exam. Here you go now. Yeah. And there are some homework questions posted and some description of topics. And the description of topics really does mean to narrow things down. There's something about linear regression, predictions and two independent samples. So you can focus on that part, the proportions, the means from one sample, so you focus on that one. ANOVA, something like conditional probability, normal probability, full charts, very much like the homework that is just coming in. Are there any big questions or types of problems that would be good to look at?
Can you go like with the regressions, which errors apply to like hypothesis?
So one of the problems related to regression on here. So let's see. And the easiest if I pull it up back over here and then go from there. So the study problems, there was one here that the description and there's, for instance, this number 9. Kind of hard to see which one. Yeah, problem 9 is one of these that has to do with that. So there's temperature recorded in degrees Celsius and amount dissolved to oxygen on 75 days in a creek in California. Higher levels of dissolved oxygen are good. As the temperature goes up, you might have more algal blooms and things consuming the oxygen. Right? And so describe the relationship between the variables. Right? So if it doesn't say specifically correlation or something, you can use ordinary language to give the impression of how these things change together. Right? So yeah, generally I think there's a negative relationship right there. It's pretty weak. Maybe a couple smaller points out here, or a few more extreme points, but with that description you can pick up on kind of just about anything in the picture, and usually a couple different things to describe. The trend is down, but it's pretty weak and would be sufficient. Now, linear regression was to predict dissolved oxygen from temperature. What is the error of the predicted regression line for this one? So here's the kind of the output, intercept, temperature estimate, then at a t-value, so a subset of what comes out of R. And the point has temperature 20.5 and dissolved oxygen. So that prediction. Right? So predict oxygen from temperature. So we get an equation, the intercept slope, and intercept and slope. R might call that a constant instead of intercept, and it gives the variable name that's x, 11.19, 11.19 minus 0.16 times x, where x is the temperature. And it says there's one point that we're interested in. Up there, the point has the largest temperature, 20.5. And dissolved oxygen of 6.6. The units of measurement are there. To speed this up, I'm just going to copy those over. So if we want to predict, we're going to put 20.5 in there. And the predicted value, you calculate that, right? 7.91 milligrams per liter of water. And the charge is kind of a low value. The error or residual prediction. So if it's actually 6.6, we predict 7.91, we're going to get an error that's negative 1.31 milligrams per liter. That area. And then it says report a hypothesis test for this whether the slope is 0. And based on the output, that's there. We're going to estimate and a standard error. It described earlier that we had 75 days there. So if we take those 75 days and those couple of things, we can do different things with it. So if our slope is negative 0.16, and the standard error for that slope is 0.06, we can test the hypothesis, is the slope equal to 0? No slope, no relationship. There's an alternative that is not equal to 0. And to test that, the estimate relative to its standard error. How many standard error units are you away from 0? Kind of implicit in this is a subtraction of 0. B minus the null value, but you don't necessarily have to put that there. This ratio, the negative 0.16 over 0.06, ends up being negative 2.67. So is that a big value or not? We're going to want degrees of freedom. Degrees of freedom for regression with one predictor is going to be 73. And if you look up in the, I'll give you a copy of the t-table. Right? And so in the back of the book, a t was 73 degrees of freedom. It's not exactly on there. With a 0.025 upper tail, for that one must be about 1.99. And t point 0.025, referenced here, of 73, should be about 1.99. And that one is less than the negative of 1.99, so we'll reject. And in this context, the slope is estimated to be negative, so I would say we reject. It's not 0, the slope looks negative. And as the temperature is going up, the dissolved oxygen is going down, and it's losing it. Another way to answer this problem would be to do a confidence interval for the slope. So you could do either one. If it says test it, you want to make a confidence interval, you could do that and then make a summary statement. So the confidence interval is our estimate plus or minus our t-value from the distribution times the standard error. So we would do memory 0.16 plus or minus, and this is where we would use the 1.99 value, and then the standard error that's given, the 0.06, and make an interval. Is that interval going to include 0, or is it going to be outside of 0? Where is that interval going to fall? So we rejected 0, so this interval has to fall below 0. All less than 0. So that's about 2 times 0.06. So it's about 0.12. So the interval is going to be something like 0.28 up to 0.04, approximately. And so we're 95% confident that the slope between dissolved oxygen and temperature is in that range. And as we get higher temperatures, the dissolved oxygen is decreasing at a rate in that range. Does that get at the question? Now, in the regression output, sometimes you get some other things. Is there another that weren't exactly asked on there? The other thing sometimes that comes with the output is R squared. Yeah.
Oh, did you just go backwards?
Sure.
So you said the confidence interval, that's the rate at which the slope decreases?
Mhm. Our estimated slope is, this negative 0.16, and we're 95% confident that the real slope, if we had the biological relationship, would be negative, in that range. Yeah.
If you're doing the hypothesis test for like the correlation row, what error would you use then? Where would you find that error?
So for the correlation, this is the one we'll use for the test.
Okay.
About the slope. If you get the same result doing this test of the slope or doing the test of the correlation. There's only one predictor. They end up being the same t-value. You would get the same t-value for those two tests, but it would be a different formula. We're going to focus on just this formula. Regression, sometimes we ask for R squared, so percent of variability. Explained by X, amount of variability in the Y variable. So this one isn't going to be terribly strong in this plot. I don't give the exact value there, but say, R squared would be about 0.2. If that number is there, then about 20% of variability would be explained in Y related to the X. In different contexts, you might think that's a small number or a big number, or kind of relative to other things that might be related to the health of the lake. This might be important. It's not zero, but it's not one, but it's not zero either. The other thing that is in that R output is an estimate of sigma. This is residual standard error. And looking at the plot of these data, what would be a reasonable, so if we put some line going through this, it might look, these are the residuals, these distances in here, these are the residuals, and so on. Right? And it looks like, many of those have a distance of 1 or 2 or 3 or less. So we could say, maybe the standard error, this thing, hypothetically might be about 0.9 for this, and it describes kind of the magnitude of those. You kind of think that plus or minus 2 or maybe a little bit more, getting most of the range of those values. Any other types of problems or questions about? Let's look at an enhancement to one of them. One of the problems, the one that is the last one, I can drop it here. Not the last one, but this 11th one. Scientists captured 2 types of woodland salamanders and measured them in many ways. One set of measurements recorded tail lengths in millimeters. There's 20 redback salamanders have an average tail length of 3.2 millimeters and a standard deviation of 0.9. And the 17 ones have that average and standard deviation. And so the problem, as it's stated there, is really about comparing 2 means. Right? We asked about that on the last exam. So the plan would be to use a statement of a problem like this and ask you, what's the confidence interval for one of the means? So that's what I stated that we would do. So in number 11 here, to make it fit what we're going to do a 95% confidence interval for each group separately. The formula for a 95% confidence interval based on a sample is x bar plus or minus some t value and then s over the square root of n. t-value is from a distribution to the 0.025 tail, and we do n-1 for each particular group. So in this case, I also have things like green salamanders, right? So we're gonna, you could look at the, well, we'll do that next. So the red ones, there were 20 of them. The average was 3.2. The standard deviation was 0.9. Degrees of freedom for our t-distribution would be 19. And looking at a t-distribution with 19, that's in the table, that value is 2.002. So at 19, 0.025, 20. So 2.0, sorry, I read my wrong thing on the sheet. It's 2.0, 2.93. That's the red one. So a 95% confidence interval for the average tail length of this group. Would be the 3.2 plus or minus this 2.093 and then 0.9 over the square root of 20. So that interval ends up giving us I don't have that one calculated, but anyway, that would be that interval. The ones that are lead colored, darker ones, there were 17 of them. The average there was 4.0, and the standard deviation was 0.7. Based on this sample size, the degrees of freedom is going to be 17 minus 1 or 16. So our t-value for this one sample interval ends up being a little bit bigger, 2.12. And the 95% interval for this type is going to be 4.0 plus or minus 2.12 times the standard deviation for that group over the square root of its 17. And that would simply be the 95% confidence interval for a single average. I'm just curious to see what these are. So let's see. Nice. Get this down here a little bit. Get R going. So we want 3.2 plus or minus the 2.093 times 0.9 divided by the square root of 20. So that's that interval. The next interval was 4.0 plus or minus or plus 2.12 times 0.7 over the square root of its sample size. And it's like that. And what do you notice about these confidence intervals in terms of their value? Yeah, they don't overlap. Right? So these means the two intervals are different. The rest of the problem shows box plots of red, lead, and green. Right? And the two we looked at, they look pretty different. So we have two individual intervals don't end up overlapping. Now I had the data from this, right? And I took some of the summary statistics from another source that simulated some data. Right? So I ran analysis of variance where I looked at the tail length versus color group. Right? And I came up with an analysis of variance table for looking at the effective group. So there was 20 red ones. There are 17 lead-colored ones. And then there were 18 that were green. So a total of 55 salamanders in the study. And color is the factor that we're looking at. There's also the error or residual in total. And ANOVA table will have sum of squares, mean square, F, and a p-value. What would it, I want to use as the degrees of freedom? What would fill in that column in this example? Yeah.
2, and then 53.
53.
No, 52, sorry.
52, yeah.
And then 54.
54, yeah. So this is the 55 minus our three groups, and this is our 55 minus 1. Yeah, those would be the degrees of freedom. When I calculated the sum of squares, there's 13.41, 29.97, and so those add up to 43.38. What is the mean square for color? Mean square for treatment? Mean square for group? Or if you don't tell me the exact value, what do we want to do to calculate it? Divide. Let's say divide the 13.41, divide by 2. So this one, 13.41 over 2 is 6.7 approximately. It turns out to be 6.70 with rounding. This one, 29.97 over 52 is 0.58. So our F is the ratio of these things. That's 6.7 over 0.58 ends up being 11.6. And that is pretty big, right? So an F distribution with 2 and 52 degrees of freedom, the 95th percentile is 3.18. Even the 99th percentile is only 5.04. And the 99.9 percentile is 7.91. And we got 11.6. So what do we conclude about these salamanders in different groups? Were these groups, was there a significant difference somewhere between these means, or were all the average tail lengths the same? They're different. Is that extreme values here? The p-value would be a very small number. You could say that the p-value is less than 0.001. So the null hypothesis is that all the means in the different groups are the same. And the alternative is that there is some difference. Because the F is so big, we're going to reject the null hypothesis. Right? And conclude that there's some difference. In particular, from the graph, it looks like the first two groups that we looked significantly different, and there might be a difference between the others. So some may be filling in a little bit of the table, kind of showing how things are calculated. If you're given a p-value in the end, an interpretation, some comment relating it to what you see in the graphs. There's one other little tad bit of information we can get out of this that's useful, is that there's a pooled variance estimate. Sigma hat squared in this case. Is this mean square error? 0.58. So our estimate of sigma, the error variance, is the square root of that. thing, and looks like it's written down. So I want to know that value, the square root of 0.58, 0.76 in there. 0.76. And in those first two groups, the standard deviation is 0.9 and 0.7. The other one, in the simulation, which I told you was 0.8. So this 0.76 is right near all those. That's kind of a compromise. Any questions? Or so the other types of problems that are on there, right, for study had, the first problem actually was something to do with regression. The second problem did comparing two proportions. The third one did a conditional probability type of tree. The next one was really comparing two means, but you could think about it as giving you the information to talk about a single mean. And then some of those repeat. Toward the end is something on normal calculation. So let's just look at that. So problem 13 on there. Okay. Okay. Okay, let's move it. Right. So this is kind of inspired by the article we looked at on Monday. So in a study of spatial reasoning ability, participants were asked to rate their level of irritation during some exercises in which they're exposed to some distractions. Suppose the irritation scores are normally distributed with a mean of 0.81 and a standard deviation of 1.15. What's the probability that the irritation scores between 0.5 and 1.5? The second question, what is the average irritation score from 20 participants is between those two numbers? So one's about the individual values and the other one's about X bar. So a normal score for on the solutions. So some solutions are posted, so you can go see more of these. It's some of these are from different exams I've taken from different courses over time. So the solutions are, photocopies from things I wrote up at that time. So let me know if you have any questions. So in this one, the data are normally distributed with an average of 0.81 and a standard deviation of 1.15. I'm writing this here because sometimes people write sigma or sigma squared. You just want to know, is it a variance or is it a standard deviation? Right? Sigma squared would be this 1.15 squared. So if I give you that number, you can take the square root of it. The probability that it's between 0.5 and 1.5. We're going to z-score it. Subtract the mean and standard deviation for both sides. Look, subtract the mean, 0.81, divide by the standard deviation. And 1.5 minus 0.81, 1.15. And this becomes negative 0.27, less than z, less than 0.6. And so this is the probability that z is less than 0.6 minus the probability that z is less than negative 0.27. And on our normal table, right, I'll give you the half of the normal table that's the positive numbers. If you look up 0.6, and it gives you a probability of 0.7257. You can't look up the negatives if I don't give you that half of the table, so you look up 0.27. 0.2 go over to 0.7, which is 6064, but it's not less than that. It's equivalent to 1 minus that, 6064, and the number, and that's 0.3321. So let's just pull up the normal table. Back over here, copy. Here's the Bohr's normal table. You could read that, right? Oh, that's the positive. I would give this positive side. And so my 0.6 number, right, 0.6 is there, and so that's where I got the, the 7257. And the other one was negative 0.27, so I looked up 0.2 and then over here to 0.7, and I got this number in here. So that's the probability you're less than 0.27. Remember, we drew these pictures for symmetries. So we really want the probability we're out here in this tail. What we can look up is 0.27. We can look up this one. And so this part up here, right, is the same as this part over here. And this area was a 0.60 something, 0.6064. And so this part up here is the 0.3936, and so this one is 0.3936. So we have the upper point was 0.6. So we took the probability we're less than this and subtracted that little part out there to get the final answer. Now if it is 20, we do basically the same thing, but for x bar, right, for the average of 20. And in this case, x bar, we use normal. The mean is the same, 0.81. But now the standard deviation that we use for this x bar is sigma over the square root of n, so we're going to use 1.15 over the square root of 20. And as shown in the solutions, then the probability that we're in that area ends up being larger. 0.879. For the individuals, it was 0.39. So the averages are tighter around the average, closer in. And so the probability goes up. But you can do it in stages where you can calculate the new mean variance, standard deviation, and then go through the normal calculation. Any questions on this homework that you're turning in today, or anybody? Did you see any other pattern in those data points in there?
There was the autocorrelation there. It looks like.
Yeah, there seemed like it would kind of go up for a while and reset and go up, and so maybe somebody's adjusted. Somebody could is doing the adjustments, working on the line, and the management knows what's going on. Somebody's fixing this thing that's drifting off into out of sync. Yeah.
Oh, could you explain number 5?
Number 5.
In the homework.
What?
In the homework.
Oh, in the homework.
Yeah.
Okay. In the homework. Right. So in the homework, I'll post solutions quite soon, later today. But these are the solutions. The plots, right? So these were the plots of the different. These are the the series 1 through 22. These are the xi values. And this is the SI values and the RI values. These are the same XI values, but one with the limits determined two different ways. One, you had to take the average standard deviation, and one doing something, an average range. And these were the standard deviation statistics, and this is the range statistics. And so nothing really seems out of line in those in particular. This is the kind of the pattern where it kind of goes, it gets reset, and there's something else going on there you might want to try to figure out. The question 5 then was this cum sum chart. Where'd that go? That's this question 5 is here, right? And so what's happening in this thing, right? So instead of taking 13 was the target, so the first point was a little bit off from the target, right? And so that's why this one's slightly negative. And the next one was also off, and so if you add those two together, it gets a bigger decrease. And then there was one that was over, so the sum of those first 3 deviations goes up, and it goes up. But what's happening later in the series, as you go along, is that the xi values are all getting low. So you keep adding, cumulatively, all these deviations that are negative, and it starts to drift off. So that gives some suggestion that even if the individual means are not, there's a lot here. There's 4 there that are below, 2, 3. Even if it looks like there's not really getting out of control, there's kind of a drift or something that might be a concern. So this plot, oops, I put it before, seems to be widening out. If it was just more random, sometimes you're high, sometimes you're low, you would be subtracting something, then adding something, and this would be much more flat. And the way the book tended to do it is you take this point, they had a way of drawing things that would go out like this, and there's a very good possibility that at some point, maybe like here if you drew it out, or here if you drew it out, that it would go outside of those bounds. So it would look like it's more of a problem sooner than those other bounds. Just kind of this other, just like residuals and regression. Sometimes you look at residuals, you see a little bit different pattern. How you scale things and put it together, different pictures show you more. So this one looks like it's going out of sequence a little bit more because it's not flat. And the 6 was the subtle patterns, right? And that's what we're talking about. There seems to be this up and down thing there that affects the means. Any other? Final, the later questions on the study problems. There was another ANOVA problem. So maybe we'll take a peek at one of those and see if that raises any questions. So in this one, I studied randomized individuals to 2 groups, stress or no stress, doing a stress video test or something, and then the other one watching the nice nature video. And they look, time to complete a task is recorded. And this is the analysis of variance table that comes up. So how many subjects were there total? Right, so if we added these together, we'd get total degrees of freedom, but that's in -1, right? So there'd be 47, 26 in one and 20, something like that, right? Is the average response time the same in these 2 groups? What do you? No. Why are they significantly different?
The F value is colossal.
Yeah, the F value is big. The P value is less than 0.05. Stating hypotheses, the average response time in the 2 groups are the same versus they're not. You conclude that they're different. An estimate of sigma from the ANOVA. Sigma would be, our estimate would be the square root of that mean square error value. There it is, which is 2.27. And if you wanted to do a confidence interval for the difference in the means in this ANOVA setting, right, pooling these things together, right, you could also be given, well, there's sigma hat. Here's the x bars, here's the sample sizes, right, here's a t-value for a certain, for 45 degrees of freedom. 45 is the error number. If we wanted to do a difference between these two groups, we take the difference of these, plus or minus our t-value, 2.014. And then this sigma hat, 2.27. And then there's the contribution of the two sample sizes. And these values from there, 7.32 and 5.55. And this gives an interval. And I have a way of sliding this up in this format. 0.426 up to 3.108 in terms of time. And so this would be a 95% confidence interval for the average difference in response time between these two groups. And is it consistent with the getting a significant result? It's all positive. There's definitely a non-zero difference, or you rejected the ideas that they're the same. These differences relative to these averages are different enough relative to all that variability to say that they're different. Right? Any? The other one is another ANOVA. Right? Same groups, but there was a different variable. It was the log cortisol, salivary cortisol levels. This one is not significant. So it does not appear to be an average between those values. Given the same type of information, you can make a confidence interval. Oops. Great. Given that information, you can make a confidence interval between the differences, and it will include zero. They won't be that much different. The averages of -0.36 and -0.35 in this sample are not significantly different. Solutions give details for that one if you want to look through that one. So I think if you get a formula sheet or a couple formula sheets, right, to have things. Make the specifics doing these type of problems. You might expand it a little bit for the things you think are important and want to remember. Right? And look at this. Look at similar problems for some of these things that were on earlier exams. We could study homeworks. I look back for the homeworks to see some types of things. And maybe 6 or 7 questions, and you'll get the time. So it takes you an hour and a half. That's kind of on par with the other hour, but there's a little bit more time for more writing if you want to express things. Yeah.
So, in terms of like the types of questions coming up on this exam, is it going to be more concentrated on SINT test 2?
Yeah. So I
Like
think
everything after.
if you put if you think about kind of go over to the top here. Right. The first page had some description of things. So if you have a linear regression question, there are 2 independent samples. This, and then conditional probability tree, and then ANOVA, and control charts and normal, that's 7. Right. So if it's kind of like that, and so if you look at the weighting, the proportions from two samples was just after the second exam. All right, but linear regression, ANOVA were after the second exam. So it is heavier toward the last third, with some in the middle, and like the conditional probability or just normal probability calculations is, But I'll show you a graph, and that's kind of something from the very beginning. You say comment on this graph, but now in the context of a ANOVA problem. So yeah, if you do the math, like seven main topics, talking about 7 questions. Not every, subpart probably will get asked. Pick something. But anyway, we'll stop there. If you have other individual questions. There's projects and homework. And I know there's 1 or 2 that wanted to finish up some for the hill, and that's all right.
But it's going to
Yep, thank you. Oh, that guy makes sense. I mean, I can't
Ask you, I know our exams are due Tuesday, but I have biochem, no, I have this and Sunday, then biochem, and then you and physics, which is a lot. I'm just wondering if I can move, so I can have a day in between exams, and move your exam to Wednesday instead of Tuesday. And since I take it in the library anyway.
Yeah, separate.
Yeah.
That seems okay.
You do that to remind yourself, well, you don't do that.
It's fine with Leslie, I'll have her email you.
Okay. Sounds good. Thank you.
So, as I was working last night, another potential project occurred to me. So I wrote a program in Java, just because I was curious. But if you look at consecutive primes and differences between them, think about you have
Good idea.
3 5s, the difference between 5 7.
It should be mine too, but I just moved this one to Wednesday.
And then this would be a histogram of that on a logarithmic scale.
Oh, okay.
Because I did
It's
it
like
normally
quite-
in the
yeah.
2s off the
It
chart.
would be nice for
but
my last exam.
as soon as I put it on a log
I
scale,
have,
like, that's almost perfect.
Yeah, it's very, very smooth.
So, and that was something which just, so I did this up to
Yeah. Is it
100 million.
depends.
Uh-huh.
I can't even, I'm so bad at using Unicode, I can't find a lot of different.
And I was like, I could have done,
I mean,
because I
Right, you
got
could have done,
pretty good.
yeah, right. That'd be a very good,
Linear regression.
kind of neat thing.
Thank you very much.
Thank you,
Pleasure.
Andy.
Yeah.
We'll see you again. Sure.
Yeah.
I still
Yeah,
get as
thank
good,
you.
I didn't get as good of a
That was
grade on
just
it as I
for
did
the-
the other one.
I don't know, I got 86 on my other one.
It could be 2 pages.
I got 94 on
You
the
get 2
paper.
pages.
I know, that's the best grade I've ever gotten on a piece of paper.
But it is more focused, so,
But-
I think,
so maybe
it's
highlighting
almost
those
switched.
portions.
Right.
I got like a
But it's,
90,
it's more
but I got
focused.
like a 95 on the
You have
presentation, like a
2
90.
pages, go
By the
back,
time I
further
presented, I
down.
was flawless, I didn't make a single mistake.
It's, should be plenty of
I
space.
don't know.
That's
What
what
did you say?
Well, we haven't gotten anything back yet, or maybe we have, but I'm not in class, so.
Yeah, because she normally details why.
I didn't know I got points off because she had 2 questions. Or one question was like, okay for me to not know, but the other one I should have known and I didn't. But I don't think that's worth 16 points.
No. Yeah, but she'll have her comments are normally pretty detailed about.
But that type of thing is, it really touches on number theory,
So it was very funny
And
when I got mine back. she was
figuring
like,
out
"How
proofs
much
that,
studies?"
is it,
You can have what?
as this n goes to infinity, would that
She's like, oh, right, there it is.
trend continue?
Continue.
Yeah.
Yeah.
Right,
Well,
or do they space out so much that it's going to distort the relationship? So, that's challenging, setting up
Yeah.
probabilities.
Well, because I went on a walk just because I was like studying for Greek and doing the project. I was taking
Uh-huh.
turns with both of those, and I was like, all right, need a walk.
Yeah.
And then that came back to me, and I was like, oh my gosh, that would have been cool. And what I could have looked at is like the first 100 primes, the histogram, then the first 1,000, the
Yeah.
first 10,000, and maybe see if the slope on the log plot is the same, but it just
Uh-huh.
kind of is moving up. And if it's moving up by a regular logarithmic interval, because that would be cool to see.
Thank you.
Yeah, and so I emailed you
Thank
R
you.
code and
See you
R.
for the exam.
Yeah, see you for the exam.
The only thing is that I was a little bit sloppy on citing. Like the only references or citing that I did was the St. Michael's College page for like what's listed as a science,
Uh-huh,
a Bachelor of Science, and what their grad programs are. That's the only.
So where did the data come from?
The data was mine.
It was
that I
yours?
did, yeah.
From-
that I did on SurveyMonkey that I still have on my
Ah.
computer and stuff. So.
Right. That's, for this, it's what people wouldn't have much more, some
Mhm.
source, a website or one article
Mhm.
or something. And, everybody could cite the textbook if they wanted to, so I'm
Right.
not too worried about that. It's just that, for individuals who chose to review a website, to do a biography.
Right, it's more exciting for that
There's a
stuff.
couple more things to make the list, so.
Yeah, the results, the regression, it's funny how all of them, it was pretty.
GPA didn't.
Yeah, and if anything, it was negative on most of them. There's only one that was sloping up, and it was by like minuscule.
Right.
But it was, I don't know, look at some, or if you're interested to look at some of the stuff, some of the R squared, the adjusted R squares, what's the range on that value?
It can go negative.
Okay, okay.
Because-
So I was a little concerned when I saw that on but it was a super, super small negative number. But I don't know.
Right, so that's basically nearly zero,
Yeah,
basically.
that's kind of what I assumed.
And so the R squared, the way it's calculated in multiple regression, always goes up. You
Mhm.
keep adding variables, even if they're junk,
Mhm.
and R squared will creep up a little bit. So it's not sensitive to just adding unimportant variables.
Okay.
But the R squared adjusted does things in terms of mean squares, and so if you add a variable
Okay.
that's not important, then it can actually go down.
Okay.
Right, so mean square error won't change, the mean square. Anyway, yeah, so it could slip
Mhm.
as you, because of related degrees of freedom. So there's kind of a built-in penalty for throwing in junk.
Mhm.
So it may be, near zero or in a multiple regression as you add new variables, it doesn't go. If that one doesn't go up, it would give some idea of where to stop.
Mhm.
Any more predictors aren't helping.
No, something I didn't do, but I think that would have been cool if I compared, because when I found male and female, both the t-test kind of pointed to how in the histogram, the histogram of the woman education income was significantly lower than the male. Oh wait, no, sorry. The male income was significantly higher than the female income,
Yeah.
and I'd be curious to know if that's because the areas of study. So like a STEM, and I kind of wanted to compare like a STEM majors with nothing, and then compare with everybody else, and then compare education majors with everybody else, because St. Mike's is kind of a big educational school, and
Right.
typically they're known for males dominate STEM and females dominate
To some degree, but
Education.
it's a lot, particularly around here, math majors are pretty evenly split.
right.
And,
Yeah.
in terms of statistics, biostatistics,
Mhm.
at the basters level and PhD level, particularly biostatistics, is majority female.
Right. So I kind of wanted to look into in a lot of it was St. Michael's alumni, or it all was St. Michael's alumni.
Right, and so,
like,
are
would it
they
change over
working
time?
full-time? Maybe some of them aren't, working part-time, maybe they're
Mhm.
they're working in education, they might like 9-month jobs.
There's something else
You
to
know,
talk
are
about.
Are they married or not?
Exactly, if they included the spouse income
Right.
with it too. But yeah, surprisingly, a lot of the data didn't really max out. I thought it didn't really max out the higher tail, which was kind of nice because, on some of them it did.
For like GPA, that wasn't as many?
No, on the
Income,
income,
yeah.
because it was capped at like $120,000. So.
Well,
some-
if you get
some-
actual incomes and then you get somebody and they're making $1 million.
Yeah.
Right, then that's hard to deal with too. You
Right.
have to take logs to get it back on a scale where, regression with one person out there, and
Mhm.
that is just gonna dominate the whole regression. And so
Mhm.
if that person got a 4.0, it looked like 4.0 is good, and if they got a 2.0, it
Yeah.
looked like 2.0 is good. So.
All right, well, thank you.
Good, yep.
I'll see you
at the
tomorrow.
final then.
Yeah.
Right.